Welcome to The Explainer. Today, we're diving into something new, and honestly, pretty elegant. It's a technique for making search better, especially in those super long documents we all have to deal with. It's called late chunking, and trust me, it might just make you rethink how you build your RAG systems.
So, let's just jump right in with a big question. For all of you out there building RAG systems, what if that very first step, the one we all take for granted, chunking our documents, is something we've been doing, well, all wrong?
Right. Let's talk about the long document problem. You know the one. You've got this huge PDF or a massive text file, and getting good relevant info out of it is a pain. The standard way we do this has a huge blind spot. It's what we call naive chunking.
And just so we're all on the same page, naive chunking is probably what you're doing right now. It's the default, right? You take a big document, chop it up into smaller, bite-sized pieces, and then you turn each of those little pieces into its own vector embedding. The key thing here is that each chunk has no idea its neighbors even exist.
Okay, let's make this real. Here's a perfect example from the research paper all about the city of Berlin. Imagine you split this document up. Now you've got these little sentence fragments floating around, like, it's more than 3.85 million, or the city is also. They've become total orphans. The connection back to Berlin is completely broken. When an embedding model sees these chunks all by themselves, it has zero clue that its, or the city, is actually talking about Berlin. All that crucial context? Poof, it's gone.
In this whole situation, it kind of sets up a classic Goldilocks problem, doesn't it? We're all on this quest to find a retrieval method that's not too simple and, frankly, kind of dumb, but also not so complex and expensive that it breaks the bank. We're looking for that just right sweet spot.
So, let's look at the options. On one side, you've got the too cold porridge, naive chunking. It's cheap and easy, but as we just saw, it can be pretty inaccurate. Then, way over on the other side, you have the too hot option, a really powerful technique called Colbert. It's amazingly precise, but whoa, the cost can be insane. And that leaves this big empty space right in the middle for, you guessed it, our just right solution.
Okay, let's talk numbers. Let's talk cost. If you use naive chunking for, say, 100,000 documents, you're looking at about 5 gigabytes of storage. Totally manageable, right? That's our baseline. Pretty cheap.
Now, hold on to your hats. For that too hot solution, Colbert, you have to store an embedding for every single token to get that high precision. So, for those same 100,000 documents, the storage requirement absolutely explodes to almost 2.5 terabytes. That is 500 times more storage. Let's be real, for most of us, that's a total deal breaker.
And this is where our story gets interesting. This is where the hero, late chunking, comes in. It's a new method from researchers at Jina AI, and it's designed to be that perfect, just right balance, giving us that high precision we want, but without that crazy, astronomical cost.
So what's the big idea? Well, it completely flips the script on the traditional process. Instead of chunking your text first, late chunking uses a long context model to read the entire document in one go. The actual chunking? That happens way later in the process, after the model has already soaked up all the context from the whole document.
Look, the key difference really is just when you chunk. The old way, chunk the text, then embed the chunks. The new way, late chunking, embed the whole document and then chunk the embeddings. That's it. That simple flip is the entire magic trick right there. Okay, so how on earth does that simple switch lead to such better results? Well, it's all about creating chunks that actually know what's going on around them.
So here's how it works under the hood. First, a long context model reads the whole document, from start to finish. As it's reading, it creates a unique context-aware vector for every single token. Now, here's the cool part. Instead of squishing all those token vectors down into one giant embedding for the whole document, you just group them up into smaller segments and then average or pool them. Each one of those little pooled groups is your final chunk embedding. And because they were created with the full context in mind, they are incredibly smart.
And the result is, well, it's kind of beautiful. To quote the paper, you get chunks where each one is conditioned on the previous ones. What does that mean? It means they're not those lonely orphans anymore. It's like every chunk got to have a long conversation with all its neighbors before it left the house.
They all carry that shared knowledge, that full context with them. Okay, that all sounds fantastic in theory, but the real question is, does it actually work? Let's put it to the test and look at the proof.
All right, first things first, let's go back to our Berlin problem. Remember those orphan sentences? If late chunking is really as smart as it claims to be, it should have no trouble figuring out that the city is, in fact, Berlin.
And would you look at that? The results are awesome. Just check out the similarity scores here. With naive chunking, the connection between Berlin and its more than 3.85 million gets a score of about 0.7. Not bad. But with late chunking, that score jumps all the way up to over 0.82. That's a huge improvement. The model gets it. It understands the connection. This right here is that aha moment.
Now, one cool example is one thing, but if you're a builder, you need more than that. You need hard numbers. So how does late chunking do on the big, standardized benchmarks?
Well, the quantitative proof is just as strong. Take the NF corpus dataset, for example, which is packed with long, tricky documents. Naive chunking scores around a 23.5%, but late chunking hits nearly 30%. I mean, that is a massive, significant jump in performance.
So, the main takeaway from all the testing is crystal clear. Late chunking just flat out beats the old way. And here's the best part. The longer and more complex your documents are, the bigger the performance gap gets. It works best precisely on the kinds of documents that give us the biggest headaches.
All right, so let's bring this all home. What does this actually mean for you, the person who's actually building stuff with this technology? Why is this a big deal for your next RAG project?
Well, the benefits are super practical. For starters, you get the low storage costs of naive chunking, but with way better results. The implementation? It's ridiculously simple. We're talking less than 30 lines of code in many cases. This means you can stop wasting time on complicated custom chunking strategies. And maybe the best part of all, you can drop this right into your existing pipeline. No other big changes needed. It just works.
And this quote from Weaviate's blog just nails it. It says, "If you want to avoid the pitfalls of naive chunking and the high potential costs of Colbert, late chunking may be a great alternative for you to explore. It perfectly captures that just right value. It's the powerful, elegant, and affordable option we've been waiting for."
Which really leaves us with a pretty cool thought to chew on. We spend so much time talking about bigger models, more parameters, new architectures, but maybe the next huge leap forward in retrieval isn't about bigger, but smarter. Could it be that elegant little tricks like this, these clever ideas happening right at the pooling stage, is that the real future of retrieval?